Okay, suppose there was a bad guy who wanted to read what was written in this letter. Back in the olden days, they could simply steam open the envelope. But now imagine that this letter is an electronic communication encrypted with a modern cipher. There's really no chance that you're going to be able to unlock or open the envelope. So what do? Well, one thing you could do is just throw the letter away and replace it with a new letter. In this video, we're going to talk about message authentication. Modern encryption gives us something that we really need in our daily communications: confidentiality. But remember, there are two other really important properties: integrity and authenticity. If you haven't already done so, go back and check out our videos about block ciphers, hash functions, and semantic security. All right, suppose Alice sends a message to Bob over the internet, and that message is intercepted by a man in the middle. Because Alice is using strong encryption, the man in the middle won't be able to read what she's saying. But what if, instead of trying to read the bits, the man in the middle changes the bits of the message? What effect does this have? In this video, we're going to explore this issue and the implications. How important is message integrity really? At first glance, it may seem like some error correction issue. In fact, as we're going to see, message integrity is so important that without it, we can't even guarantee confidentiality. If Alice were to, say, encrypt a photo and send it to Bob, and along the way, the man in the middle modified some of the bits, as we saw in our encryption video, it would corrupt the plaintext. So Bob would end up with a garbled-looking image. Let's start by looking at the effects of message modification. If a man in the middle were to flip a bit of the ciphertext, what effect is that going to have on the plaintext? Well, if we're using a one-time pad, the effects are very straightforward. Flipping a bit of the ciphertext will have the effect of flipping that associated bit in the plaintext. So the one-time pad provides no inherent message integrity, but that's okay because we don't use the one-time pad anyway. All right, now let's see what happens in a block cipher in counter mode. Counter mode is a lot like the one-time pad, except that the pad is being generated by encrypting a counter using a block cipher. Like the one-time pad, this result is then XORed with the message to create the ciphertext. So again, if a man in the middle were to flip one bit of the ciphertext, it would have the effect of flipping that bit in the plaintext. Things are a little bit different in the cipher block chaining mode of operation. If you flip one bit of the ciphertext, it will affect all of the bits in that block, flipping each bit with 50% chance as per the avalanche effect. So by flipping a single bit, you're basically destroying the entire plaintext block. However, because cipher block chaining feeds the ciphertext forward into the next block, flipping one bit of the ciphertext has the effect of flipping one bit of the plaintext in the next block. So in each of these cases, flipping a bit of the ciphertext has the effect of flipping a bit in the plaintext. So what this means is that the attacker has a way to make linear modifications to the plaintext without knowing the key. And this is a vulnerability the attacker can exploit. Now you might be saying, so what? If a man in the middle starts flipping ciphertext bits, it's going to mess up the plaintext, and Bob's going to notice, right? Well, before we dive into the practice, let's look at the theory. Let's look at the adaptive chosen ciphertext attack, the CPA2 game. As it turns out, if there's no message integrity, we can win the CCA2 game. Recall, in the CCA2 game, the guesser picks two messages, any two messages they'd like, and they submit it to the challenger. The challenger flips a coin. The outcome of that coin toss selects one of the two messages to encrypt. Now, if the challenger is using a block cipher in cipher block chaining mode, they would pick a random initialization vector and send the ciphertext and IV back to the guesser. Now recall, in the CCA2 game, the guesser is allowed to make decryption queries after receiving the challenge ciphertext. The only catch is they cannot submit the challenge ciphertext itself. But what they can do is submit modified versions of the challenge ciphertext, anything that's just different. So why not just stick a random block at the end of the message and submit that to the challenger. The challenger looks and sees that it's not identical to the challenge ciphertext and agrees to decrypt it. And here's the trick. Changing ciphertext blocks later on in the message has no effect on blocks earlier in the message. So when the challenger decrypts this query, the last plaintext block will decrypt to something random, but it doesn't matter. The point is the first plaintext block will be identical to what the challenge ciphertext had encrypted. The challenger will send this 2-block plaintext back to the guesser, and the guesser will look at the first block, and that will represent the plaintext that was chosen. The guesser always wins. This system is not secure under adaptive chosen ciphertext attack. Okay, so you can win the CCA2 game if there's no message integrity. So what? How likely is this to be a problem in practice? How likely is it that Bob is just going to start decrypting things that he receives on the internet and sending them back to people? Not really likely, right? Well, not so fast. In practice, no. Bob is not going to just start decrypting things for random strangers. However, Eve is smart. In practice, she's going to be able to provoke Bob into revealing information, kind of like a poker tell. She's going to be able to slowly and methodically collect these little bits of information and put them together into something useful. But before I can show you how this works, let me start by telling you about something called padding. As we saw in previous videos, block ciphers work on fixed length blocks. So what happens if your plaintext message does not evenly divide the block length? And if the last block of the plaintext is smaller than the block length of the cipher, we're going to have to do something. So for example, imagine that you were using AES, which has a 16-byte block, but you only wanted to encrypt an 11-byte message. What do? Now the first temptation might just be to add 5 more bytes of zeros to the end. But what happens if the plaintext itself consisted of zeros? We need some kind of unambiguous way that Bob can recognize what's message and what's padding and remove the padding. Well, one way we can do it is to use a padding standard called PKCS number 7. It works like this. First, determine how many bytes of padding your plaintext needs. We'll call this number n. Next, add n bytes of padding, and the n bytes are each going to be the number n. So if we needed 5 bytes of padding, we're going to add 5 bytes of the number 5. When Bob decrypts this message and sees the padding, he knows exactly how to remove it. And the deal is we always add padding. That way it's unambiguous. So what happens if our plaintext is a multiple of 16? We don't need to add padding. But remember our deal, we always add padding. So what we can do is add an additional block of just padding, 16 bytes of the number 16. Okay, so what happens if you decrypt a message and discover that the padding is wrong? What should you do? Okay, imagine that Alice and Bob are communicating. Alice sends a valid ciphertext to Bob, but along the way, Eve swaps out the valid ciphertext for just some random garbage ciphertext. Bob decrypts this ciphertext and gets a random looking plaintext. The last byte is not valid. What should he do? He's going to have to behave differently somehow. The difference might be overt. Bob returns an error message to Alice, or it might not be so overt. Simply, Bob takes different amounts of time to handle valid versus invalid messages. But as it turns out, Eve is going to be able to exploit this. Eve is going to find out one way or another whether or not the padding was valid. And she's going to be able to use this information to her advantage. Whether he means to or not, Bob essentially is going to behave like a padding oracle. Eve hands Bob ciphertext, and Bob tells her whether or not the plaintext padding was correct. Now you might be saying, well, who cares if Eve can figure out if padding is valid or not. The problem is padding oracles can be turned into decryption oracles. Let's see how this works in CBC mode. If Eve modifies the last byte of the second last block of ciphertext, that modification will wind its way into the last byte of the plaintext. Eve doesn't know the last byte of the plaintext, but she can indirectly infer it by whether or not the padding is correct. Essentially, Eve is going to be able to brute force the last byte of the plaintext by modifying the last byte of the second last block of ciphertext. She's going to make a guess about what that plaintext byte is, and she's going to modify the ciphertext in such a way that if her guess is right, it will result in a plaintext with valid padding. She's going to create this modified message, send it to Bob, and then observe whether or not he reacted as though the padding was correct. If the padding wasn't correct, she's going to modify her guess and send another ciphertext to Bob. She's going to repeat this over and over again until she finds a modification that Bob doesn't react negatively towards. Once she's confident she's figured out the last byte of the plaintext, she'll repeat this attack again on the second last byte. Once she has that information, she'll repeat the attack for the third last byte, and so on until she's recovered the entire message. So Eve is going to be able to figure out a plaintext byte in approximately 255 queries. So in a 16-byte AES block, Eve is going to have to make on the order of about 4,000 decryption queries. 4,000 queries is actually less than it might seem, and real implementations of this attack can recover an entire plaintext block in a few seconds. Recovering the plaintext of a single block would be enough to recover the authentication token for a website that you're visiting, allowing the attacker to log in as you. So we need to figure out some way to stop padding oracles. After decades of padding oracle attacks, there's really no point to experiment with trying to make the software not reveal this information. The attacker will be able to tell that difference one way or another. So what if there was a way that decryption itself never actually went through if the ciphertext wasn't somehow valid? And what if it was hard to decide whether a particular ciphertext was valid without knowledge of a key? This brings us to something called message authentication codes. The idea is we're not just going to encrypt the message, we're also going to apply some kind of authentication mark or stamp or seal of approval. And the idea is we're going to make it cryptographically difficult for someone without knowledge of this key to apply a similar stamp or seal of approval. Then, if Eve tries to swap out a valid ciphertext for one that she injects herself, it will be missing this stamp or seal of approval, and Bob will be able to detect it and just ignore the plaintext. So if we return to our eavesdropping game, the idea is we were just trying to make it hard to recover a plaintext given a ciphertext. Now in the chosen plaintext attack game, recall the guesser has the ability to make encryption queries. So the way that we defeated the chosen plaintext attack was we allowed a single plaintext to go to many possible ciphertexts. So if the guesser could make an encryption query this time, that doesn't matter because the next time that same plaintext gets encrypted, it'll map to some other value. Well, with the chosen ciphertext attack, the way that we're going to defeat it is for not every ciphertext to be valid. In fact, we'll set it up so that the overwhelming majority of ciphertexts are not valid, and the only way that you can find one that is to know the key. Like encryption, message authentication codes are a family of 3 functions. The first function is a key generation function. Just like encryption, it accepts a security parameter and produces a random k-bit key. Also similar to encryption, the message authentication code signing function will accept some arbitrary length message and a key. But unlike the encryption function, it will produce a short fixed length output called the MAC tag. The verify function accepts an arbitrary length message, the MAC key, and a MAC tag, and it will output a single bit. Either yes, this message matches this MAC tag for this key, or no, it doesn't. Now you'll notice that the message authentication code sign function produces a fixed length output. We've already looked at functions that produce fixed length output in cryptography, hash functions. In fact, we can use hash functions as a building block for message authentication codes. One thing hash functions don't have natively is a way to incorporate a key. We can't just take the key and stick it at the front of the message and then hash it, otherwise there are attacks. And we can't take the key and just stick it at the end of the message and hash it, because there are other attacks. But what we can do is take the key and stick it at the front of the message and hash that, and take that result and stick the message in front of it and hash that to create our MAC tag. This construction is known as a hash-based message authentication code, or HMAC. Okay, so we have these message authentication codes. How are they applied to messages? Do we MAC the plaintext? Do we MAC the ciphertext? How does it work? Well, there's actually several different ways we can approach this. One common approach is the encrypt-then-mac approach. The idea is you create a ciphertext from a plaintext, and then you apply the MAC function to the ciphertext itself. Notice that the encryption key and the MAC key are different and independently generated from one another. Otherwise, certain attacks exist. Encrypt-then-mac as a configuration is actually widely used in TLS today. But another approach is the mac-then-encrypt configuration, where the MAC function is applied to the plaintext to produce the MAC tag. And then the plaintext with the MAC tag are all encrypted to produce the ciphertext. In this configuration, the ciphertext containing the encrypted plaintext and MAC tag are sent over the internet. Remember, if Eve tries to modify the ciphertext, she's going to end up modifying the plaintext somehow. This will introduce a mismatch between the plaintext and the associated MAC tag. And when Bob verifies the plaintext against the MAC tag, they won't match. Okay, so let's apply this idea back to our chosen ciphertext attack game. Once again, the guesser picks two messages and sends it to the challenger. The challenger flips a coin, picks one of the messages, and then creates the challenge ciphertext from it. The challenge ciphertext is returned to the guesser. Now the guesser is free to make decryption queries. Remember, they can't ask for the challenge ciphertext itself to be decrypted, but they can modify it somehow and ask for that to be decrypted. Imagine that the challenge ciphertext was 0111. The guesser could try to create a trivial modification to the ciphertext by appending a block. In this example, we'll append the block 00. But remember, the second block of the challenge ciphertext contains the encrypted MAC tag. So if the guesser attaches another ciphertext block to the end of this ciphertext and submits it to the challenger, when the challenger goes to decrypt, they're going to take the first two blocks of the plaintext and put it into the MAC verify function. They're going to take the last block of the plaintext and interpret it as the MAC tag. And then they're going to use the MAC key to see if those two plaintext blocks were consistent with that MAC tag. Now, in this 2-bit example, they're going to have a 1 in 4 chance of hitting the jackpot. But if it was a 128-bit cipher, they would have a vanishingly small chance of finding the right tag. And that means the challenger is going to reject the decryption query because the ciphertext was invalid. And because the guesser isn't going to be able to come up with a valid ciphertext, they're not going to be able to see a valid decryption. And therefore, they're not going to be able to squeak out any information about what the challenge plaintext was. So this is how we defeat the adaptive chosen ciphertext attack game. Now let's go back to our padding oracle example. The idea is that Bob is not even going to look at the plaintext unless the MAC tag was valid. And therefore, he's not even going to look at the padding to see whether it was valid or not. And this makes Eve's life much harder. Without message authentication codes, approximately 1 out of 256 randomly chosen ciphertexts are going to have valid padding. But with message authentication codes, that probability goes way down. Okay, so let's take our encryption and message authentication and put it together into one package called authenticated encryption. Once again, we're going to have a family of 3 functions. The key generation function is going to accept a security parameter, and this time it's going to produce an encryption key and a MAC key. The encryption function is going to accept a plaintext and the encryption and MAC keys and produce a ciphertext, an initialization vector, and a MAC tag. And finally, the decryption function is going to accept a ciphertext, a MAC tag, an initialization vector, and the 2 keys. Now here's where the magic comes into play. The decryption function will only ever return a plaintext if the MAC tag is valid. Otherwise, it will simply produce an error. Authenticated encryption is going to protect developers by making all the hard design choices for them. The cipher mode of operation, the message authentication code, the MAC configuration, and what to do if something goes wrong. All of these things will be handled for you inside of one convenient API. All right, let's look at an example. One of the most commonly used forms of authenticated encryption is something called AES-GCM. Now this is the AES block cipher, and it is being used in counter mode. It's also using a message authentication code based on multiplying numbers in Galois fields called G-hash. And finally, the G-hash MAC is being applied in an encrypt-then-mac configuration. AES-GCM is used all over the internet. Next time you go online, click on the padlock icon and see if you can see what cipher it's using. Okay, so we learned an interesting lesson in this video. Confidentiality is extremely important, but without message integrity, we can't have confidentiality. So the way that we win the chosen ciphertext attack game is with message authentication codes. All right, that's it for now. If you enjoyed this video, don't forget to hit like and subscribe, and we'll see you next time.